Hi, hello. Welcome to everyone that have joined the webinar and
And
also to those watching the recording. My name is Shai. I'm a math professor at Tel Aviv University and also a proud investor and active chairman at tasq.ai. So a few words about Task. It's a deep tech company that provides a platform and services for data operations and labeling. So it's really the backbone of the AI industry. So Task has a unique approach in this space where complex labeling tasks are broken up using codeless workflow tools into micro tasks and then distributed to the global crowd, where the labelers are trained and tested. So the better performing labelers are targeted for specific tasks and the less performing are pruned out of the system. And then multiple judgments are collected through an adaptive sampling process that Vadim will expand upon. And it's done until some statistical significance is reached. And then what we do is we take all these micro tasks that have been labeled and collect them all back to provide the full labeling solution. So this unique approach actually allows to obtain labeling at a very high quality, which is of course very crucial in this industry. But at the same time, it allows scalability beyond what a dedicated in-house or a third-party labeling task force can provide. So that's a few words about Task, and Vadim will expand later on, of course, about the system and the capabilities. So we're going to dive into the webinar, and keep in mind, please, that it is going to be somewhat technical. So Vadim and myself have done our best to provide examples and visualizations. So it gives some intuition, even if you're not a data scientist. And so I'll start by providing an overview of the model-centric AI first, and then I'll introduce some key concepts from the data-driven AI, and then I'll hand off the presentation to Task's head of AI, Vadim, to discuss data-centric AI with the Task platform. At the end, we'll have a short Q&A session. And so if you don't have a chance and there's some questions that are left unanswered, so please feel free to reach out directly to either myself or Vadim after the webinar. Okay, so let's get technical. What is model-centric AI? And so we have models, specifically deep learning models, in some cases that are trained using a given training data set. So with model-centric AI, the data set is sort of fixed, and then there is a research phase for finding the best architecture, giving all sorts of trade-offs, okay? Which is how many data scientists you have on the project, how much hardware you have available, and so forth. What does best mean? Well, I mean, it's very specific to each project, but the simplest example is that you have your data set, you're training your model, and then you have some held out validation set that the model basically is not trained on, and you're looking for the best model, the best hyperparameters, the best epoch where you will achieve the best accuracy, highest accuracy on the validation set. Now, there's a zoo of models we can choose from, of course, going all the way from the simpler machine learning models to the deep learning models. So logistic regression, random forest, support vector machines, gradient boosted, and then going into deep learning, we have the convolutional neural networks, the transformers. And even if you do choose one model, there's all these hyperparameters to choose from. So in deep learning, it would be the number of layers, the number of feature maps or neurons at each layer, the type of nonlinear activation, and so on and so forth. So if you're a data scientist focused on model-centric AI, the data set is fixed, and you're going through all these options of models, trying to optimize the model on your given problem. Now, so we're going into the details of this model-centric stuff, and basically the first interesting question is a basic machine learning model sufficient, or do I need a deep learning model? And I think that in most 95% of the cases, data scientists just try and see what comes out, okay? No, but the point is, and this is something we're researching at Tel Aviv University, that there is an absolutely mathematical foundation to this. And there's actually a mathematical foundation that unifies signal processing, machine learning, and deep learning. And the approach that we take is based on analysis, mathematical analysis, and specifically high-dimensional function spaces and approximation theory. These are all, high words. Let me give simple examples. Let's take two example data sets. I'm taking first the Titanic data set. It's a very famous data set, very interesting, where the data set, the row of the data set is basically a person that boarded the Titanic, and then then the features are like age, gender, class of ticket, where they boarded, and so forth. And the output Y variable, the response variable, is survival, did they survive or not? When we look into this high-dimensional feature space, input feature space of the Titanic data set, and we visualize it, we see clear clusters, okay? And so jumping a little bit ahead, what I'm saying is that for this type of data set, basic machine learning models will work well. Because basically what they do, they go through the feature space and they actually segment it out and look for these clusters. Whether, on the other hand, when we go to a second very famous data set, the MNIST data set, which is basically a data set of images of handwritten digits. This is the most basic and famous data set for deep learning. And we visualize the input feature space. And what is the feature space in this case? It's composed of the image pixels. So think of taking the pixels of each of these small images here and concatenating the rows into a long vector. And basically, and so what is visualized here, projected in some way to 2 dimensions, is each point here in this cloud, in colorful cloud, resembles one of these input images. And we see here spaghetti in the input feature space. We see here that we have here two images from two different classes, the class of 2 and the class of 3, but they're very close in the feature space. What does that mean? That means that basic machine learning models will not work well for this data set. And yet it is so simple in some sense, and it is known that you can achieve very high accuracy on this data set. So the idea, what's happening here is this, is that if in your input feature space, you have good separability, clustering, and again, coming from analysis, you have high function smoothness in some sense, then the classical machine learning algorithms will do well on a data set like the Titanic. And here is the punchline. Where does deep learning come in? When you are in a spaghetti situation, when in your input feature space, there is no clustering, there is no structure. What does deep learning do? With the forward feed layers, basically, the role of deep learning is to perform automatic feature engineering and from layer to layer, improve the clustering to unravel the spaghetti. And again, from analysis side, improve the smoothness of the given function until you see, and this is exact rendering that has been done, you see that basically at the final layer, the MNIST data set is similar in a position similar to the Titanic, enabling to classify with high accuracy. Okay, so this is lesson number 1 in model-based AI, the difference between ML and DL. Now, basically, with our research at Tel Aviv University, we could go deeper into the black box and analyze the performance of inner layers in deep learning. So let's see an example. Here we see a graph where on the x-axis, we see the layer number of some architecture called the VGG. It doesn't really matter. We won't go into the details of that. On the y-axis, we see our mathematical measurement, our mathematical notion of the performance of the layer, of the function smoothness. How much did we unravel the function at this layer? And now what we do, we basically play around with one hyperparameter, but we could, of course, play with any hyperparameter, and we play with the hyperparameter of the non-linearity applied at each layer. And so we see that the famous Rayleigh nonlinearity basically does a better job at the inner layers. It sort of helps unraveling better than the other nonlinearities. Now, this analysis that you see here in the graph is performed only using the model and the training data without observing the testing data. And we see this amazing correlation between the ability to perform mathematical analysis on the inner layer and the actual results at test time. So there's a correlation which shows that this works. Okay, we could also do this when we look at a question like how many layers do we need in a neural network to get high accuracy? And this type of graph analyzes that. I will not go into that. But we could do more. We could basically take this understanding of what needs to take place in the inner layers and add to the known loss functions that are used when we train deep learning, and specifically models that do classification. We can add loss functions that encourage this function smoothness, that encourage this clustering, and in fact, achieve better testing results. So basically what we see here, of course, we're going through this very quickly, but the idea is this: take any data set, be it for computer vision or NLP, take any model, whether convolutional or transformer, okay, and here we see actually results for transformers, and use and add these loss functions that are based on our research, and you would actually obtain better, you will improve your models, you will improve the testing accuracy of your models. And basically you can go to my website and see some papers that explain that. Cool. So that's a little bit about model-centric approach, but what are the problems? What are the issues in cases where you leave the training test as is and you play around with the model? What could be the problems? So let's again try to visualize it in simple manner. So issue number one is when the data set has inconsistencies, you're going to have huge issues with your model. Let's see very simple two examples. Now here on this side, on the left side, we see a consistent data set. Very simple, univariate, but simple. In what sense is it simple? We see here that, and in what sense is it consistent? We see here that all these neighboring x values going from 0 to 1 all have a y variable 0. So neighboring x's have the same y. Then there's a jump here at x equals half. And then all the x's that are greater than half have a response variable y equals to 1. But neighboring x's on this side also have the same y. So this would be a consistent data set. And in fact, of course, the simplest model in machine learning, logistic regression, will capture this data set, train on it very quickly, and figure out that this is the sort of the borderline. What's happening here on the right? Okay, this example visualizes a case where basically for very nearby x's, you have very different y variables. And in real life, okay, this simple example speaks to a case where you have labelers labeling very differently, assigning very different classes to, say, similar images or similar pieces of text. So these are the inconsistent, samples of the training data set, the blue points. What is the orange line? The orange line is your deep learning model, okay, stretching and pulling itself to overfeed the training data. And indeed, it can do that, okay? And we'll see in a minute the implications of that. And so, so these are the examples of what happens when you have inconsistent data. Now, basically, if you're a data scientist, and let's see here this a little bit better on sort of real data. So take an image, a computer vision data set such as the CFAR, okay? And then take a reasonable model, deep learning model, and train on the CFAR. And this is this blue line here, okay? You see the loss reduced as you go through the training phase, okay, through the epoch of the training until you reach zero loss on the training data, okay, not the validation of the test, the training data. The network has enough capacity to fit the training data. Now go and mess up your data set and train and just use, you see here, random labels, train again the model. Okay, it's going to have a harder time, but it's going to overfit. So it's going to get to training loss. Okay, why? Because it is doing this stretching and pulling. Okay, now you're a data scientist, you're training your model on the training data, you achieve zero loss, you try to validate your result on some held out set, you get a mess, you don't know what's happening. Okay, so and you're stuck. So this is, in simple terms, one of the problems when you do a model-centric approach and you just leave out the data set and you don't touch it. This is a situation you can encounter. Now, we can, again, with our research, we can actually quantify this with this function space approach. We can take very well-known data sets. We can start messing them up, messing up the labels, 10% of the labels randomly chosen, 20 and so on. And our approach can, as you see here, the smoothness, so to speak, goes down because we are able to analyze the smoothness of this orange function, so to speak. Of course, with deep learning models, it's all in very high dimensions and it's more complex, but we're actually quantifying the smoothness of the inner layers of the model. And this is how we understand inconsistencies of the data, and we model it as problematic or highly non-smooth functions. Issue number two, when you do the model approach, is that, and I think a lot of data scientists have encountered that, is that you spend, you spend a lot of time trying to optimize the model, trying out various configurations. And I mean, it takes up a lot of precious hours of data scientists and then a lot of compute power. And in many cases, all to achieve very small improvements in inference performance, okay, in production. So that was model-centric AI, and now let's start talking about the data-centric AI. Conceptually, what we should think about is actually fixing the model, okay? So basically just think of a case where you have, say, a computer vision task. And to be honest, in most cases anyway, I mean, computer scientists and deep learning researchers are pulling off from the GitHub, off-the-shelf models in any case. So assume your task is, say, image classification. And so you take some encoder type of architecture with some residual blocks and some fully connected layers and the final softmax layer. So you take this basic model with a few residual blocks, you keep it fixed, or maybe you're doing image segmentation. So you take a basic unit type of architecture, you keep it fixed. And then what you do is you work systematically with the data. And so you do better labeling, better training of labelers, multiple judgments, and I'm not going to go into that because Vadim is going to speak to that. Or potentially you add more data, you augment the data by generating synthetic data, or enriching the data sets by applying all sorts of transformations. And so I've had experience with this method since I would say 2017, and it works beautifully. Now, but of course, don't take my word for it. I mean, we have our mentor, Andrew NJ, that through 2021 has spoken quite a few times about this approach, this data-centric approach. And he came up with these 5 tips that are excellent, and I would like to bring them up. And later on, Vadim will map them to the tasq.ai system. So, tip number 1, make the labels consistent. We saw, I tried to show examples, what happens when they're not consistent? What happens to the model that needs to pull and stretch and perform poorly later on during inference? And then use consensus labeling to spot inconsistencies, okay? And that comes in with the task system through the adaptive sampling that Vadim will talk about. Clarify labeling instruction by tracking down ambiguous examples. Certainly what is happening inside the task AI system. Toss out, tip number 4, toss out noisy examples. More data is not always better. And in many cases in production, if you go through samples of the data set, there's all sorts of noise there that is irrelevant to the project and needs to be pruned out, just to give a simple example. And just to strengthen this idea, the deep learning models, AI models, if you give them this type of junk, it will just take them off trail. It will give them a bias. They will not necessarily know what to do with it. Tip number 5, use error analysis to focus on the subsets that need to be improved of the data. And I think that, especially in 2021, it's like the rise of data-centric AI. I mean, it's clearer to the community that the data scientists are spending more time on actually getting the data, cleaning the data, gathering the data, improving the data, while basically most of the community are using off-the-shelf models. And so it's coming clearer that basically the data is the gold. Most of the issues and most of the work needs to go to improve the data. And so, okay, I will hand off with this to Vadim.
Okay.
Go ahead, Vadim.
Thanks, Shai, for amazing theoretical introduction to what I will talk about now. So now actually I will go to business area of what Shai was discussing. So I'll talk actually about the algorithms that we use to ensure the quality and about how approach the tasq.ai takes to be into this data-centric AI industry. So, but to give you more ideas so you have a better understanding about the algorithms and how they fit in the process, I just want to give you a better context about what tasq.ai is and actually expand on what Shai said in the beginning. So basically we come up with the term like codeless enterprise data operation platform. And the idea behind this is actually the platform on which you can do different types of operation with the data. So you can do data labeling, content moderation, also about data collection. And one of our services is having access to the worldwide crowd that can do lots of small to average tasks like in parallel on their mobile devices. And we also our all company is actually a platform to do all those services. But I guess one of the unique feature of ours is that our data-centric capabilities are integrated in the process. And they actually connected, I would say, in those two concepts, having like workflows and micro tasks. And I think it's kind of a big differentiator from us to different companies that data-centric capabilities fit like natively into the process. And let me explain what I mean by that. So on the left, you would see a diagram that on average, we can approach any labeling tasks from something very simple to something very complicated. So we take one big complicated labeling tasks, let's say it's object detection, and split it into small micro tasks. And I'll just give you an example. Let's say we have a big image of the road on like cars and traffic, and first we'll ask multiple people just to put dots on all the objects, like on the lights, on the cars, on the pedestrians. Then the other people would actually put the bounding boxes on top of those dots. Then we would ask a different set of people to actually do the classification. And like we can do also a hierarchy of classification and filtering in this process. And the interesting part of it that it can be first of all split in the parallel, and the approach that it's granular, those tasks are granular and isolated, which means that we can actually train people on specific tasks and understand where they fail in it. So the one person can be good on finding objects, the second is very good at classification. And then it's easy to find the, I would say, weak spots of the process, because it's like the process online and you can actually do consensus in every step, meaning that you can find the consensus in the object detection, then on bounding box, then on classification. And this actually gives you a much better consistency because you actually evaluate the quality all along the process. And basically on the go, you can find ambiguities and filter the noise. So that's the process of how we approach the labeling. And I would say this is like the UI, how it looks like. You actually like create all the processes, then add different tasks along the go and just set up the process of labeling. But actually today I want to focus on the process connected to the about the crowd. You guys, give me 1 second. I think there is something wrong with the presentation. I'm very sorry. Something on here. Yes, here we go. So we'll focus actually on 3 steps of one of our platform, which relates to crowd, that we have access to the worldwide crowd, and we actually show the algorithms how we assess the workers, the quality of them, and how we do it all using the statistical models, and actually show the quality of the annotation, how we actually achieve the consistency and the quality. And we'll start actually with the real use case of our clients. So I'll show you the examples how those algorithms improve on the baseline. That this is like a security cameras project that gives you the project that can be used for object detection and classifications, like for people and cars. And it can be used not only to give the data to the model, but it can be online process to actually use the crowd to evaluate the model performance and actually provide the weak spots back to the model. And it can be online process of training and improving. So
Vadim, you're not moving with the presentation. You're on slide 22. Sorry, you're stuck on the slide.
I'm stuck. Okay, 1 second.
Okay, yes.
Yeah, okay.
And going to presentation mode, yes.
Yeah. Okay, thanks. So yes, this is like the example of the security cameras or the project that I will show the examples and the results that we use the algorithms for. So it's like used for object detection and also for model validation. But before we jump into the process of where the algorithms fit into the data-centric capabilities, I'll just show you the overall process of the labeling, like how we approach, like, on the every steps. So almost every client starts with a, they provide the instruction and the small list of the ground truth. And what we do afterwards, we actually do the training of the labelers. I mean, I would say this is a standard approach for almost every company. But afterwards starts the process actually of labeling on the real data. And those we actually feed the algorithms. First, we use the algorithm that we call adaptive sampling, and I will show you the details about it later, to achieve the consistency of the labels. Afterward, we understand that the actual labels are consistent, we estimate the quality, the confidence of the labels. And in the case that we are not confident, I mean, that after the labelers did the labeling using the consensus, so we ask multiple judgments with, if we know that the answer is consistent, but it's not confident, and what is the difference between confidence and consistency, I'll tell you in a minute, we actually will give to some like high tier quality assurance to understand what's going on. Maybe this is something, a use case that the ground truth that the client provided doesn't cover. And this is, to be honest, a very common use case. I'll tell you why. I mean, the client would give you like 10 to 50 images that they see that should be like these instructions, but in the real life, when you label like 10,000 images, there's definitely going to be use cases that the original instruction does not cover. So having this loop is actually very important. But also the algorithms that evaluate the labeler performance. And we also have like expected labeler performance. This is actually also important point, that if you get the quality of the labeler, how good he was trained only here, when you know the ground truth, you're actually missing the opportunity to understand if the labeler got lazy, or maybe he gave to work with his little brother because, I mean, this is a remote work and you actually cannot track everything. So having the algorithms that can estimate the quality of the labeler on the go, on the unseen data, can be very crucial and actually improve the quality of understanding the confidence of the annotations. And if something goes back, you can actually go back to the retraining or even reject from the system in the worst case scenario. But once the loop is finished and we know that we got the high quality annotation, they are automatically added to the rating. And interestingly enough, what Shai mentioned before, that our process actually natively is connected to the tips that Andrew NG gave like a year ago. That, for example, if you go to consistency of the labels and consensus labeling, this is all done in this part of our algorithms section, like actually doing the sampling, asking for more and more judgments until we're sure that the labels are consistent of the high quality. And when we know that the confidence is not high enough, there's like automatic loop to possibly detect the ambiguous examples and also filter out the noisy data automatically. And actually, when we get some errors, we have this loop, and also to enrich the ground truth, because we know that there might be some mistakes in there. Okay, let's jump into the algorithms themselves. And the first one will be a single sample confidence using the Dirichlet distribution. So this is the algorithm that represents the quality of annotation when we have only one image or one audio clip, and then we have multiple judgments, and we understand how confident in the consensus judgments when we ask for many people to label it. But let's start with a very simple example just to check your intuition. Let's say we ask 7 people to give a class to an image A, B, and C. And we have 2 scenarios. The first scenario when the 4 people voted for A, and the second scenario when 3 people voted for B. Oh, in the first scenario. But in the second scenario, 4 people voted for A, 2 for B, and 1 for C. Would you be equally confident that the A is correct in both cases, the first one and the second one? I'll just give you a second to pause, just to think about it. I'll pause. But I think the intuition would tell you that in the scenario 2, you would be more confident that A is correct. And the intuition is very simple, because in the scenario 1, the 3 people voted for B, and it's like the B pushing harder against the A. So here we have less confidence that A is correct. There's still some more chances that maybe a couple more votes would come to B. But here, the A would stay stronger against B and C. And math proved this intuition. So it's like not only our intuition, there's formula behind it. And it's just based on classical Dirichlet distribution, this concept And I will not dive deeply into the formulas, but I'll just give you a hint. So we have like a vector of samples of alphas, and alpha 1 is how many people voted for class 1, alpha 2 is how many people voted for class 2, and alpha k is how many people voted for class k. And actually the distribution, the Dirichlet distribution, is like a continuous probability distribution, and it's connected to the family of the gamma functions. And this actually, the density of this distribution is described by this formula, and it's like normalized by beta function. And those are formulas that provide mean and covariance metrics. I will not, it's not, I would say, explain all the details of the math, but what I want to show you the actually the visualization of those, of this distribution and how it relates to this previous example. So those visualizations should be like easy and intuitive. Let's go one by one. So the use case number 1. Let's say we have 2 people voted for A, 2 people voted for B, and 2 people voted for C. And the darker the density, the higher probability it has. So we know like 2, 2, and 2, it's somewhere in between. So there is no, the probability doesn't go to the edge of A, B, and C, so it stays in the middle. So we're not confident that it is likely to be one of the classes. But as you can see, the variance, the blob, is big. So if you would ask for more judgments, there is some probability that it, for example, would nudge closer to A. But the variance is big, so it means there is some chance that it could happen. But let's say we sample more judgments, and eventually it would be like 8 people for A, 8 people for B, and 8 people for C. We still in the center, still not confident it's A, B, and C. But now the variance is much smaller. So what does it mean? It means if we sample more, if it's like 50, 50, and 50, there is no chance that this blob will go to A, to C, or to B. So it's clear enough that we reach the consistent results, but it doesn't give us any confidence if it's either of the classes. So actually we can estimate the variance of this blob of the probabilities and say, okay, now there is no need to sample more. We know that our labelers do not agree, so maybe we need to clarify the instructions, or maybe it's just a noisy data and there is no clear answer. So this is actually a very good indication when there is no need to sample for more judgments. And now let's look at the visualization of our previous example when we have like 4 people for A, 3 people for B, and 0 people for C. So it's clear that it's far away from C, and it's somewhere in the between, in the middle between A and B, and closer to the A. And the variance is rather big. I mean, the visualization doesn't, maybe it's not very intuitive, but you can see. So it's basically down and below. But if we change like to 4, 2, and 1, you would see that the blob got closer to A and also a little bit up to the C. So it's actually between somewhere like 30 and 40% that it would be B, and more about like 70% that it would be the A. So the confidence that the probability that the class is A is higher here than here. So our intuition is proved. Now the question comes, how do we actually estimate this variance of this blob to understand, do we need to sample more or not? And this is where the covariance matrix comes into play. We actually estimate the norm of this covariance matrix, and the bigger the value, the higher, I mean, the less confident we are, I mean, the less consistent we are. So it means that we need to sample more. And I showed you like all the possible norms of the 7 judgments. And you would see like in 430, it has the biggest value. So the algorithm would suggest us actually to sample more to know that it's still likely to be changed. And for example, here we have like 6 people for one class and 1 people for the other class. It has, I would say, the least amount of norm. I mean, and when all people vote for 7, it's just 0. So it's very, very clear. And now the interesting algorithms could be discussed here. When we can put the threshold, or what is the good enough variance that we're confident in the results. So those are the additional algorithms that I will not discuss here, but actually it's an interesting point about, the balance between the quality and the profit, and the, for example, quality and the speed of the labeling. So this is, like all the variables that can be manipulated easily on the process, but we're not covering it here. Let's move back to our examples. And I actually ran a test job asking people like for majority to get the answer value using the majority vote, and the red line is actually the quality of the annotations, and here the option like majority vote of 3, 5, 7, and 10 people, and also the possibility of using this adaptive sampling technique. And as you would see, the quality is the same as asking the 10 people to vote, but it requires much less judgment. So it's actually a very nice improvement, like in the reduce of the amount of work. So now the overall project can go much more effective. And the interesting use case when, like talked about between consistency and confidence, there were some use cases when, we sampled enough judgments, but we didn't reach enough confidence. And when the high tier QA would go over those like low confidence examples, there's actually a pattern that emerged. When the people and the car overlap with each other, there's actually a high confidence that the labelers would disagree. So we understood that actually in our instructions, it wasn't not enough of the use cases that covers this specific scenario. So this actually like automatic process that we can actually enrich our ground truth again and give to better labeler training. Now, let's move on to the second part, is how you can actually understand the quality of the labeler to do the two things. First of all, we can use actually to even make stronger the algorithm for adaptive sampling. We can enrich it with the confidence of quality of the labeler. And also we can actually use it to retrain the labelers if they didn't get the instructions, or maybe, like incentivize them or punish them based on how good they performed. And again, let's jump into the very simple use case. Again, 7 people give judgments and 4 out of 7 vote for class A. I guess this is a no-brainer that in the second scenario, when 4 good labelers vote for A, much more likely that A would be the correct answer than the use case 1. If I would give, like my rule of thumb, like, estimation, in this scenario, I would say it's like at most 50-50 case, but here it will maybe 80-20 or even 90-10 that A is correct answer. So the difference can be very drastic. The question, how to actually online estimate the quality of the labeling and actually automatically change the process. So the algorithm itself, it's based on the expectation maximization, and the David and Skin, whose researcher the algorithm name came from, it was developed in 1979, so it's already 43 years. And this is the baseline algorithm. And afterwards, like for those 43 years, there's lots of algorithms that were built on top of it with more advanced ideas how to detect labelers that won't intentionally hurt the system, how many labelers who are just the spammers. So there's lots of advanced techniques built on top of this. But this is, like I would say, the baseline algorithm, which used still nowadays. And I'll give you the explanation about it, and we'll not jump into more advanced stuff today. So the algorithm actually is, even though the complex formulas might look complicated, the nature of it is very simple. It's actually iterative algorithm. And how it starts, you go check the majority vote of each consensus in the data set, or maybe in the batch, like in 100 images. And you start with saying that the majority vote is supposed to be the correct answer. So this is our initial state. And then we iteratively will change these decisions until we converge to some, final, stable state. And there are 2 steps that actually interchange: maximization step and expectation step. What maximization step does, first it calculates distribution of the classes. I mean, what the percentage of class of labels belongs to A, what percentage belongs to B, and what percentage belongs to C, and so on and so on. And afterwards, for each labeler, we create his error rate, confusion matrix. I mean, what does it mean if you don't know what it is? Well, for each labeler, we ask how often he confused A and B and A and C, and how often he confused B to C and B to A. So this is a matrix of his mistakes. And then we use the class distribution and his error rate in expectation step just to use the classical Bayes theorem to understand what is the probability of this object, of this image, to be the specific class. And now, because we will use actually the probability back then in the maximization step, the distribution would be changed. And then it means that we left the stable state and we will actually iterate until we reach the converged state. Maybe it was too vague, so I prepared an example for you, just to go step by step. And maybe this diagram would look a little bit complicated to you, but we'll go slowly on a very simple example and you understand what I mean by that. So let's say we have initial labeling of 5 images and we have 5 labelers doing those 5 images. And for easy understanding, I'll just give you a hint so you understand what's going on with those labelers. So it's easy now to catch. So the labeler number 1 and 2 always give correct answers. Labeler number 3 made a mistake on image 1, so he put an A here. The labeler number 4 made 2 mistakes here. And the labeler number 5 is our worst labeler. He gives everything vice versa. He gives every time mistake. Now, how do we catch it? So we start with a majority vote. And the interesting thing that would be because 3 people voted for A on image 1. So the majority vote would be A, which is an incorrect answer because, as I told you, labeler 1 and 2 always give correct answer. So the class distribution would be 40% for A, which is two images, and 60% for B, 3 images. Then we would do actually the confusion matrix, like true positive and false positives and true negative rates of each of the labelers. And then we do the bias theorem, having the class distribution and the confusion matrix to understand what is the probability of each class being a certain label. And you would see for image 2, 3, and 4, it's 99% for its own class. But for image 1, it's 96% of being an A and only 4% being a B. So it's not 99, it's 96, meaning that it's already left its stable state. And if we repeat the process of maximization and expectation again, you would find that class distribution changed a little bit. So we have 39% for A, because it's 96 here, and we use it, the probabilities, and 61% for B. And also, confusion matrix also changed a bit. And then we repeat again, and again, until we reach the convergence. And there's 20% for A, which is only the last class, and 80% for B. And here we would see that it's 99% here. And the confusion matrix of each labeler also changed, in which the last labeler on the true positive and true negative rates got 0. So now we can use those confusion matrices to identify, some algorithms to get the worker qualities, simple formulas or advanced formulas, it doesn't matter. But this is actually the point where we come to understand that how good is the labeler. So let's move on and just to our actual example of security cameras. And here's actually I plot you each of the labelers that participated in this job and how many judgments he made. And you would see that some of the labelers had a very low expected quality, even though all of them passed our training. This is an interesting point. And actually, you would see that none of them made many judgments. So the actually people who did most of the judgments have a good quality. So the system is able to catch them and not let them actually continue until they're well trained. So this is something that interesting concept that you can see on the real use case. And I also want to give you some examples, just to see how the algorithm of expecting labeler performance could help doing the faster annotation. So in the use case, when we had a majority vote of 10 judgments, there are 2 scenarios when the majority vote only 4 out of 10 votes to do the classification. But when we actually do the adjusting to the labeler's performance, the algorithm would tell us that the 4 labelers are one of our best labelers that actually did the classification. All the rest were not good enough. So overall, the quality, when we estimate the confidence, it would be very high. So 4 votes from those good labelers is enough to be sure that the annotations of the high quality, and we don't need to do additional round of QA and can automatically send them to annotations being ready. So this is it for those algorithms. I would say the baselines of the algorithms. There's more to tell, but not in this webinar. And I'll just want to give you a quick summary. So there are lots of algorithms connected to like data-centric AI that can automatically and even on the online manner can ensure the consistency and the quality of the labels. And this process can not only ensure the quality, it can automatically catch both noise and ambiguity without actually needing to go over the full round again. It will be just on the go. You would know that something is wrong there. And having this algorithm will reduce the work amount, so the process will be faster and cheaper. And the process that tasq.ai uses can automatically have the, I would say, looped process of improving the instructions when the client gave initially. So you could catch something is wrong on the go and don't have to reannotate all the data. And then you can also detect both good and bad annotators, and then either use like stick and carrot to penalize or incentivize them. But as all the good managers know, that incentivization is much better. Okay, guys. Thanks a lot. I guess it's time to do some Q&A.
Right. Okay. Thanks, Vadim. Well done. Okay, so we have some, let's see, some questions here. We have two questions. So I'll take the first one, Vadim, you take the second one. And the first question is, when should a person stop improving the model and start focusing on improving the data? So I guess my answer would be something that seems to work, is take an off-the-shelf model and see what it brings, and then start actually working on the data first. And then only at the point where you understand that you have data of high quality and the model is, the model performance is saturated, your off-the-shelf basic model is saturated in some way, only then, take a snapshot and start working on the model. So that would be my answer, to start with a data-driven approach first. Cool. The second answer, Vadim, you can take that one if you want, is adaptive sampling. In which use cases is adaptive sampling good for?
Okay.
Vadim.
So actually, adaptive sampling can have a wide variety of use cases. So I just showed you the classification example, but it can be also used in ranking examples or every continuous when you need to put a number. The same way it can be used for bounding boxes. If we would talk about segmentation use cases, it would be a little bit tricky, but this is possible, and this is something that we also do. The only issue that doing the full segmentation can, asking for 10 or 50 judgments of doing segmentation can be actually, for some companies, prohibitively expensive, but the algorithms allows this as well. So I don't see any limits on using the algorithm. The question is actually, I would say, cost performance ratio, but for simple to average tasks, this is a native way to go, and I would suggest every company that use consensus should use those algorithms.
Okay, and so there's another question from the attendees that asks about the data we're collecting on the global crowd and the confidence we have in their annotations. Is this data private or can be shared and so forth?
Let me take it. Actually, this is something that we already do share, and some of our clients actually requested, not only about the confidence of annotation, which actually some of our clients use it as in the loss function to train their models. So it's additional value, like the confidence annotation, but also the quality of the workers can be shared as well. So this is, like I say, an open data that we can send through the API. So it's like a native process. And I see we have another question. Can you design microtasks only for cognitive tasks like NLP or vision or other cases like financial fraud? I don't see any issues of designing micro tasks for any process whatsoever. So I would say this is a native capability to do for whatever use case you have. So it is the matter of creativity. And I would say like what actually we do at tasq.ai, we have like a very unique and process comes. We can design two different workflows of those micro tasks and see which one performs better. So this is something only just a kind of like an art. So yes, you can do every possible business use case.
Okay, and then there's another question from the crowd. Yeah, Vadim, about the Dirichlet distribution. Yeah.
Okay. I'll just read it out loud. When you've talked about Dirichlet distribution, you have mentioned confusion matrix. How do you measure accuracy, precision, recall, and F1 score? I'm not sure that I mentioned confusion matrix alongside with Dirichlet distribution. So about the accuracy, precision, and recall, I guess the confusion matrix is used for estimating the worker quality during the
perhaps Vadim, the question is about the covariance matrix, like maybe of the Dirichlet distribution. I don't know.
Yeah, so if you can actually clarify the question, it would be better, but I'll try to answer as I understood it. So for the confusion matrix is only about the precision and recall for expectation maximization algorithm, the David skin. And this is how they use it to estimate the worker, not the worker quality, the part of the algorithm. But to be honest, when we have a skew in the data, those metrics can be a little bit when we have like 99% for class A and only 1% for class B, so it can be an issue. So there's some advanced on this algorithm to use additional
Did we lose Vadim?
Yeah.
No, you're here. Okay.
Yeah, I'm back.
Okay.
So what I'm saying, we actually measure the variance, and using this variance can be actually to identify the consistency. And afterwards, after we actually identify the consistency of the results, there's actually value of variance and how it reflects to actually the metrics, so the accuracy, precision, and the recall. Those are the additional algorithms that I don't want to talk about right now. So the very naive way to do it is actually check on the use case. But this is something that I would say sometimes could be time prohibitive. So this is something you wouldn't do, but there's some algorithm that can actually automatically allow you to identify how the consistency is consistent. It's like, what is the probability that the value would be changed? So there's some additional algorithm, they're more advanced, and specifically didn't cover this in this presentation. So I guess
that's all for the next webinar. So okay, we've run out of time. Hopefully this was helpful, interesting. And as I said at the beginning of the webinar, if you have any more questions, any comments, feel free to reach out to either Vadim or myself. Thank you very much for attending today, and see you at the next webinar, everybody. Bye for now.
Okay, guys. Bye-bye.